okay, you're writing. So we had set of data. We did an exam. So we get back to the static numbers, fixed numbers, and then we expand it into random variables. We have done an exam, okay, and 400 students, and I calculate the values, and the average was 60. Okay, so the average was 60. But all the students were very hardworking, and they did a bonus homework, let's say, which was 10 points. So what I did, I add 10 points to every single student in the class. Now, what will happen to the average? Before that, I did an exam, and the average was 60. Okay? Now, because everybody has done the bonus homework, so I add 10 points to everyone. What happens to the average? Yes, because I add everyone 10 points, so it is like the average has been added by 10 points and it has been moved to number 70. So if I am adding a number, the average will be changed. Now, imagine before I add the numbers, I calculate the expected, the variance to see that how the students are varying, and I got the variance to be number 5. In other words, I draw the PDF or the distribution, and I got this triangle, okay? Now I have added these 10 points extra to everybody, and we understand that the average is moving. The average now becomes 70. What happens to variance? The variance will not be changed because the distance or the difference, the number of students who are less than average and the number of students who are greater than average has not been changed because everybody has been equally moved. So in other words, if this was the distribution before, we have the same type of distribution here, but it has been just shifted. So if we are changing or we are translating the random variables or the data that we have, it won't affect on variance. So if I am adding some number to the variance, nothing will be changed. The variance will be fixed. However, the expected value will be changed. The expected value will be changed. In other words, the sigma square of x is sigma square of x plus minus alpha. It won't change the variance, but it will change the expected value. Keep this one in your mind. What if I multiply my random variable? Remember, mu of x plus minus alpha is mu of x plus minus alpha. Expected value is not changing. But what will happen if I multiply by a number? In other words, I did an exam, and the class was not good, and the average, let's say, was 20 or 30. Then I said that, well, this is not good, and something should happen, or whatever. We decide to multiply all the grades by 2. So what will happen to average? The average was 30. I multiply all the numbers, all the grades by 2. So what will happen to the average?
It will be 2 times bigger.
Yes, it will be 2 times bigger. So it will become, let's say, 60. So if I am mu of beta x is beta multiplied by mu of x. But what about variance? This time we are not only shifting. In other words, we are not saying that the number of students with this distance, which are let's say 2 points less than the average value, will not be kept. It will be changed. Why? Because I am multiplying. Previously, the average was 30, and I had, let's say, one student who was 29, so it was 1 point less than average. Now, if I multiply everything by 2, I see that that student now will have 2 points difference from the average. So I am changing the distances. So what happens to variance? It will change. I mean, we don't use the word increase because I may multiply with a smaller number. But how much? Imagine I have 3 values. 1, 2, 3. What is the average? 2. What is the variance? 1, because the distance is 1. Now I multiply all the numbers by 2. What will be the average? 4. What is the variance now? I have now 2, 4, 6. What is the variance?
2.
Variance is 2. Or is it 4? It's 4. Because it is this distance squared. When it was 1, 1 squared is 1. But when it's 2, it's now 4. So can you generalize and say that if I am multiplying by beta, what will happen to variance?
Beta squared.
And prove it. And I think it is one of your homework questions anyway. Think about it. And not only think about it, you have to prove it. And the proof is very simple. You go through the formula and you get the results. And again, this one needs to be proved. But you go there and you see that it will be cancelled out. Or the similar thing for the for the mean can be studied. I have to upload the homeworks. Now we want to talk about discrete probability distribution. If the random variable x has k equally likely outcomes, then the discrete before I fill it, I have k equally likely outcomes. What type of distribution do I have? Forget about that x is a random variable. Imagine that I have an event, I have a process, and I have 4 equally likely distribution. I have a die, which I can draw it, and I have 6 outcomes, and the probability of each of them is 1/6. Which type of distribution is this? It's called a distribution. You should know it, you should know it, you should know it, you should know it, because we talked about it last semester in the pattern recognition. And and you should know it. I mean, the hyperbola, this is one of the things that you might have seen it in the high school, but it's the world's simplest and most famous uniform. So then the uniform, the discrete uniform distribution is given by notation f of x semicolon k indicates k is a parameter, indicates a uniform distribution, and k is a parameter showing the total number of possible outcomes. So, as you noticed, we want to talk about a few very important distributions, and then we get back and do some examples about them and see how we can use it. The next one is binomial distribution. Binomial. What do you understand from the binomial distribution?
There are two possible outcomes.
Yes, it's only binary. It's two possible outputs. It's called the Bernoulli trail. The Bernoulli trail, the definition is that if an experiment has two possible outcomes, such as success and or fail, it is called Bernoulli trail. Now, in computer science, it's one of the very famous trails, and binomial distribution is very, very useful distribution. Because almost in all aspects of computer science, we are facing this type of distribution, this type of trail. Even if we go more advanced, like talk about pattern recognition and classification, everything can be decided and can be displayed as a two-state situation. Imagine you want to do a face recognition. Okay, and in this class we have, let's say, 10 students, right? So it means we have 10 classes which we need to recognize the faces. So what we do, we can always divide it into a way of making a binary decision. And how can we do it? We have 10 faces, and we want to make it, we want to represent it as a binomial distribution. In other words, I want to do 10 person recognition by using yes and no. How can I do it?
Compare the picture with every 10 pictures and then it's either is the person or not.
Yeah, I mean, we can start like this. Is it person 1 or not? So it's binary, yeah, right? So, is it person 2 or not? And there is a way that we can actually make a multi-class classifier by using a binary classifier. And if you remember, we talked about multi-class SVM last semester, how we can develop it by using a binary SVM, and we show the tree. And so what we do is, it's very important because many things that we have can be expressed in this form. Many things that we have, we can express it as a failure or a success in order to proceed. Now, let's do a further definition by talking about what is a Bernoulli process. There are 4 parts. The experiment consists of n repeated trails. Each trail is a Bernoulli trail. So we have n trails and each of them is binary, yes or no, success or failure. The probability of success denoted by, so from now on we use the probability of success denoting it by P, remains constant from trail to trail. So it means that if you have a process that we say the probability, it's a yes and no question, okay, it's a success or failure, and we say that if in trail 1 the probability of success is P, when we go to trail 2, when we repeat this process, still the probability of success is P. We understand that, imagine the probability, the process is this, the probability that we have balls, lots of colorful balls, let's say 4 balls in green, 4 balls in blue, and so on. And the success is you get in a green ball, okay? And the first scenario that I want to tell you is this. I don't see anything, so I have 16 balls and I know 4 of them are green. I put my hands in and I pick up one ball and it is yes or no, green or not green, and I throw away the ball. And I do it, let's say, 3 times. Now, I have not written the number 4, but at the moment, is it a Bernoulli process?
At the moment when you don't throw it away, it is.
I do throw it away.
Then the next time it won't be.
Yeah, then it is not a Bernoulli process because the first time I have 16 ball and the probability of success is 1 over 4, right? 4 over 16, 1 over 4. Now I pick up one and I throw it away and assume that this is not green and I throw it away. And I pick up another one. What is the probability of success now? It changed. It's now 4 over 15. Or maybe if the ball that I have thrown was a green one, it will be 3 over 15. But the fact is that it is changing. So if I throw away the ball, it's not, It definitely has n repeated trail. It is definitely a Bernoulli trail because it's yes green or no not green. But the probability of success, the P, is changing. So in that case that I'm throwing away the ball, it is not a Bernoulli trail. However, if I pick it up, I say yes green or no green, and I put it back, the probability of success is still the same and nothing will be changed. What will happen if I pick it up, it is green, I put it back. But if it is not green, I throw it away. Abdulaziz, is it now a Bernoulli process? Why? Yes, this time again the probability changes because if I pick it up and it is green and I put it back, of course the probability of success will not change. It will be still 1 over 4. But if I pick it up and it is not green and I throw it away, the probability of success will increase because now it will be 4 over 15 instead of 4 over 16. Now, and then fourth one is the repeated trails are independent. Now, it means that, let's get back to my example that I pick up a ball and I put it back in. So I am not throwing anything away. So the step 1, 2, 3 are satisfied. Now, are picking up a ball depending on the previous event? In other words, if I put my hand in and I pick up a green ball and I put it into the box again and I pick another one, does it depend on the previous value? No, so it means that each of the trials are very independent from each other. That is Bernoulli. But sometimes we understand that it may depend on the previous values. I mean, weather is a very good example not to be Bernoulli. Because let's say we have 4 states of weather and the probability of, let's say, if yesterday was sunny, well, I mean, in Estonia they are very independent, but I mean in general the probability that yesterday was minus 20 degrees, today become 20 degrees is we understand it's not possible because the today's temperature depends on what happened yesterday up to some degrees. So it cannot be considered as Bernoulli. You can of course define lots of constraints and make something which is not Bernoulli to look like Bernoulli, but this is not the case in here. So, the number 3, remember, it means that the samples are being placed back into the sample space. In other words, we don't exclude them after we have picked them up. Now, we will do an example, but it's a kind of a long example, so we'll do it on the next session. But we talk about, we started with the binomial. So we talk about what is a Bernoulli. Let's do the definition for binomial. And then tomorrow we will solve examples on Bernoulli and then example on binomial. So a definition for binomial distribution is the number x of success in a Bernoulli process consisting of n Bernoulli Bernoulli trail is called binomial random variable if each it's called binomial random variable. Now, if each trial can result in success with probability of P and failure with probability of Q, then the probability distribution of binomial random variable is called binomial distribution and is given by, so if I have a binomial random variable, the distribution that it has is called binomial distribution. And in order to have a binomial random variable, that random variable should be a Bernoulli process. Now, if the probability of success is P and the probability of failure is Q, what is Q? 1 minus P, right? 1 minus P. So then, P of x is equal to x for binomial distribution is shown as B of x semicolon n and P. N tells us how many trails of Bernoulli trails we have. So we have n Bernoulli trails. And P is the probability of success. So it is equal to n combination of x, P to power x, Q to power n minus x, which is written as n over x multiplied by P to power x multiplied by 1 minus P to power n minus x. So let's step into here when we were talking about a uniform distribution. How many parameters in a uniform distribution we have? One. In order to give you a full description of a uniform distribution, I need to only tell you k. So here we have only one parameter. Now, if I want to tell you the whole information about the binomial distribution, how many parameters do you need? 2. We need to know what is n, we need to know what is p. So here we have 2 parameters to describe what is the uniform, the binomial distributions that we have. Do we need to know about q? No, because it's 1 minus p. So if I know p, I can always calculate q. Now we have to do an example on Bernoulli trails, Bernoulli process, and then we do an example on binomial distribution. And you can see that when we have a binomial type of distribution, we start to see how, in example, how we are describing what is success, what is failure. One thing about binomial distribution is that it's easy, because it's easy to see what is P and what is Q when you are defining your scenario. So you will see that later when we are talking about more complicated type of process, more complicated distribution, we will get back and we see that how we can calculate those ones by using binomial distribution. Because no matter how many alternatives, how many outcomes you might have, you can always express it as a binomial form. Remember, imagine I want to categorize things into the 4, so I have 4 categories, class 1, class 2, class 3, and class 4, and I can always do this. Is it class 1? Yes, then we have class 1, and if it is no, then we will see, is it class 2? If the answer is yes, then it means we are class 2, otherwise we check, is it class 3? And the answer yes, which means we are class 3, and the answer no means we have 1 class left, which is class 4. So as you can see, I do the classification into 4 classes, which definitely not a binary number, I mean a yes or no, by using the yes and no questions. And this is very popular in the computer science when you are developing some algorithms, because developing a binary classifier is easy. Maybe it's even very fast, and you can always extend it into a multi-class one by using this type of logic. Now, we use this type of logic when we are talking about different type of processes later, how we can express it by using the binomial distribution. Of course, when we have a uniform distribution, it's even much easier, so you don't really need to express it by using the binomial distribution. Now, do you have any question up to this point? If you have no question, I will promise you to put some homework for today, and we will start by solving some sample examples for Bernoulli process and binomial distribution tomorrow.